Welcome back to our searching and sorting algorithms. Today we're diving into MergeSort algorithm, which is one of the most efficient sorting algorithms and a classic example of the divide and conquer approach. So what exactly is MergeSort? So MergeSort is a powerful and efficient sorting algorithm that uses a technique or method called divide and conquer. Here's how it works. First, MergeSort will repeatedly split the array into two halves. This dividing process continues until we are left with subarrays that each contain just one element. Next, it begins merging these two small pieces back together. Each merge step combines two halves into a larger sorted section. Finally, we will continue merging all the subarrays until we end up with a fully sorted array. This step-by-step process is what makes MergeSort so effective, ensuring that the array is sorted by the time every piece is recombined. Okay, now let's look at the code breakdown for our MergeSort algorithm. As you can see, here's the code for the method called sort. And to implement MergeSort algorithm, we would need a function, a main method, and a utility method or a helper function. So, in a nutshell, the helper function would be the function that deals with the merging of the two subarrays. So now let's look at the main method called sort. Since we are going to use the recursive divide and conquer technique, we will have to add a base case. Otherwise, our code will run infinitely and somehow reach to the point where there will be a stack overflow error or an exception. Okay, here's the base case indicating that we're going to be repeatedly dividing the array into two halves until the length of the array becomes 1. Okay, let's move on. Here we can see the indexes left, right, and mid. Left is simply the left index of our array, which always starts with 0. The right will be the last index of our array, which can be easily calculated. And for the mid index, we are going to combine left and right and divide it by 2. And we're going to obtain the mid index because we will be needing it to create two subarrays, the left and right, and divide the array into two halves. As you can see, here are the two subarrays. So if you're wondering what J is for, it's going to be used when adding values to the right subarray. So here is the for loop that will be used to populate both subarrays. So inside the loop, there is a condition that checks if there are still elements that are needed to add to our left subarray. If there are, we will add them to the left subarray. If our left subarray is already full, we will continue on to add the elements onto the right subarray. Okay, next we can see the recursive calls. So first of all, we will call the sort method on our left subarray recursively to divide into two halves. Next, it will be followed by a recursive call to the right subarray to do the same thing. But in the last line, we can see the recursive call to our utility function, which will merge the two subarrays that we have got into an array, into a larger sorted array to be exact. Let's move on to the helper method, which is merge. Okay, here are the pointers or indexes that we are going to use. L is for the left subarray, R is for the right subarray, and I will be used as a pointer for the array that we will be merging into. Next, we can see a while loop. So this while loop will merge the two subarrays into one, but there is one catch. So this while loop will break or end its process if either the left subarray or the right subarray reaches the end. So it doesn't actually add the elements from both of the subarrays into the array. It will end if one of the subarrays reaches the end. Inside the loop, we can see the condition check looking for a smaller value within the two subarrays. If there is a smaller value, we will add them first, and it will be followed by a smaller element. And keep in mind that we will have to increment the indexes of the subarrays after each addition, and the index of the index, which is the pointer for the array, will also have to be incremented after each iteration. So if you're wondering what these two while loops are, they are going to check if there are still elements that are left in one of the subarrays, and if there are elements left in the subarrays in one of the subarrays, we will add them onto our array that we are merging into. So for example, the while loop, the first while loop will be checking if there are elements left in the left subarray. If there are, we will keep on adding the elements in the left subarray onto the array that we are merging into until we reach the end. The second while loop will check if there are still elements left in our right subarray. If they are left in the right subarray, we will keep on adding them onto our array that we are merging into until we reach the end. Now let's look at the visualization example. As you can see, here is an unsorted array with many different values. So by definition, we will recursively divide the array into two halves, which are the two subarrays, until we reach the length of the array of 1. So until there is only one element left in each subarray. We divide it into two halves. Recursively, it will be divided, and it will reach the point where all the subarrays becomes all the subarrays contain only one element. Okay, here is the complete picture of our recursive division process. Now let's look at the merging process. So starting from the left corner, as you can see, the left subarray will have the element 12, the right subarray will have the element 21, and we will get the array that we are merging into. So first we compare 12 with 21 and add the element which is smaller onto the array that we are merging into. So 12 goes first, followed by 21. Okay, moving on, we can see the two subarrays. The left subarray contains the elements 12 and 21. The right subarray contains the element 15. And we will repeat the process of merging. So 12 compared to 15, 12 is less than 15. So we add it first onto our array that we are merging into, followed by 15, lastly followed by 21. Okay, so here we will stop the merging for the left side, and we will continue merging the right side of our array. So on the right side, we can see two subarrays. 32 will be the left subarray, 10 will be the right subarray. We will compare these two and see that 10 is a smaller value. So 10 goes first onto the array that we are merging into, followed by 32. As you can see, this part is now sorted. And now we have the two subarrays, left subarray with containing the values 10 and 32, with the right subarray containing the element 16. As we compare it, 10 goes first, followed by 16, followed by 32. Here's the last step of our merging process. We will merge the two subarrays, the left one and the right one, into a completely sorted array. We compared 12 to 10. 10 is less than 12. So 10 is definitely going first. We compared 12 to 16. 12 is less than 16. We compare 15 with 16. 15 is less than 16. And we compare 21 with 16. 16 is less than 21. We compare 21 and 32. 21 is less than 32. Now, as you can see, we have finally reached the end of our while loop that runs as long as both L is within the bounds of the left subarray and R is within the bounds of the right subarray. So after the ending of our while loop, there will be two more while loops that will that will handle the situation. So once this loop finishes, the two while loops will check if there are still elements that are needed to be added. So since we have one element that is going to have to be added into our array that we are merging into, from the right subarray, we will be adding the last element onto the array that we're merging into. So now we have finally got a completely sorted array by using the methods and processes of the MergeSort algorithm. Now let's break down the time complexity of MergeSort. So MergeSort algorithm works by recursively splitting and merging subarrays. So understanding its time complexity requires looking at these two main steps: the divide step and the merge step. So for the divide step, the MergeSort divides the array into two halves, and it keeps on splitting each half until we have subarrays with just a single element. Since each division splits the array in half, this process continues for about O of log n, log n times. Sorry about that, it's not O of log n, it is log n times. Let's move on to the merge step. Next, during the merging phase, each pair of subarrays is combined back together in a sorted order. Merging the elements at each level takes O of n times. It is because we visit each element once during each merge, during every merge. Now for the total complexity, since we have log n and O of n, so log n will be the levels of recursion, and the merge step takes O of n times. The total complexity of MergeSort is O of n log n. So What's great about MergeSort is that this time complexity applies to all cases, best, average, and worst. This consistent performance is what makes MergeSort so reliable for larger datasets. Lastly, we will talk about the space complexity. The space complexity of MergeSort algorithm is O of n, primarily due to the extra space required during the merging process. The auxiliary arrays, which can be also stated as the helper arrays, which are basically the subarrays. The auxiliary arrays are the arrays that we use to temporarily hold elements while it merges subarrays. Since this array holds the same number of elements as the original array, it requires O of n space. If we implement MergeSort recursively, there is also some space used by the call stack. The maximum depth of recursion is O of n. The maximum depth of recursion is log n. So the space used by the recursive calls is O of log n. However, the dominant factor here is the O of n used by the auxiliary array for merging. As a result, the overall space complexity of MergeSort algorithm is efficient in terms of time complexity. We do need to account for the extra space it requires during execution. Now let's write the code for our MergeSort algorithm. So the main method will be sort. Okay, we will have to put in our parameters. Okay, since it's going to be recursive, we will need to add a base case. Since we are going to divide the array into two halves repeatedly until we are going to reach the state where our subarrays are of length 1. So if the length is less than or equal to 1, we will return. Now we will return. Otherwise, we will now calculate for our middle index and then start dividing the array into two halves, namely the left subarray and the right subarray. So left would be 0 because all arrays start with the index 0. And right would be the array.length minus 1. So here we will calculate the middle index divided by 2. Now we get the middle index. Now what we're going to do is create our subarrays. Left subarray. Okay, new array of integers with the length of mid plus 1. Okay, now let's create a right subarray. New integer array with the length of array.length minus left subarray.length. So it's going to be the remaining elements. Okay, so that will be, here will be the index that we will use when adding elements to the right subarray. Now we will create a for loop. Okay, now we will start adding or populating our subarrays. If I is less than left subarray length, we will keep on adding. Left subarray. We will add the elements from our array to our left subarray, and if we have added the elements to the left subarray, we will use the index j to add the elements to the right subarray. Okay, so if the elements are still in the array, if the elements in the array should be added to our left subarray, we will keep on adding it until the left subarray is full. Then we will use the index j. Else we will write subarray of j. So keep in mind that we are going to use the index j to add elements into our right subarray. But we will keep on using the index I to indicate the element in the array that we are going to sort. Don't forget to increment j once we have added the element. Okay, now we are finished with the for loop, and we will move on to the recursive calls. First, we will recursively call the dividing method on our left subarray. It will be followed by the right subarray, and lastly we're going to call our helper function or utility function, which we haven't declared it yet. We will name it merge, and we need a couple of parameters like the array that we are going to merge into, the left subarray, and the right subarray. Okay, we will call merge recursively. So the array that we are going to merge into will be simply the array that we're going to sort, and left subarray goes here, followed by right subarray. Great. Now let's write the merge method or our utility function, which will actually merge two subarrays into one array. Okay, let's start. So first I will declare some variables that will be used as indexes or indices. So I0 and of j, L for the left subarray and R for the right subarray. I will add some comments here. The array that we are merging into for the left subarray, for the right subarray. Okay. So now the indices are now declared and assigned. We will start with a while loop. While L is less than left subarray dot length and R is less than right subarray dot length. This indicates that we are going to run if both indexes L and R are less than their respective arrays length or their respective subarrays length. So keep in mind that this loop will stop when either the left subarray or the right subarray reaches its end. After that, the two while loops that I've explained in the Google slides will come in handy. Okay, firstly, we're gonna have a condition check. If the left subarray of L is somehow less than the right subarray, or so if there's a smaller element in the left subarray, it's going to be put into the array that we are merging into first. So array of I is going to be the element, the smaller element to be exact. After that, we will have to increment L, and I will be incremented after each iteration. So else we're going to add the elements in the right subarray, of course. Don't forget to increment our indices or indexes after each assignment of values. Okay, now we're going to add the two while loops that will handle the situation whenever our while loop stops or breaks. So, well, if there are still elements left in the left subarray, we will add them all onto our array that we are merging into. So, if I will be subarrays value from the index L, increment both. Okay, so in case there are still elements left in our right subarray, we will do the same thing. R plus plus I plus plus. Okay, so now we can say that our merge sort algorithm is done, but we will have to test it to see whether it is correct or not. We'll call the function on our test array and finally print the array out to see if my solution works. There we go. As you can see, my solution works. And fun fact, MergeSort algorithm is stable, meaning that if there are duplicates in the array, they will maintain their order even after sorted, unlike quicksort, which seems to work similar to MergeSort, not totally, but kinda similar, because they are both using the divide and conquer technique. And to sum it up, quicksort is not stable, meaning that the duplicate elements or the duplicate items in a list won't maintain their order after sorted. But for our case in MergeSort, they are going to be in the same order even after sorted. So this will be it for today, guys. If you want to see more videos on algorithms and data structures and want to know more about searching and sorting algorithms, which is a series that I'm actually doing right now, make sure to leave a like, subscribe, and make sure you give me some suggestions whether I have to improve my videos, because I'm just starting my YouTube journey recently.